No, we have to add switch on, switch off. Why? What? What happens with our TV? Okay, dear colleagues, let us start our seminar. This week we will have two seminars about the Q-operators. Today, Bart Vlaar will discuss Baxter Q-operators for open spin chains, and tomorrow we will discuss the similar Baxter Q-operators, but for the true Synars Schneider system. So let us start our seminar now.
Thank you very much. Okay, so this is joint work with these two gentlemen, Alec Cooper and Robert Weston, who are based at Heriot-Watt University in Scotland. And there's two papers in the archive. The first one is actually in JPhys 53. The second one is under review. And so I will start with, let's say, a survey of closed spin chains. Okay. So let's start with an algebra, a unital associative algebra. And suppose you can think quantum affine SL2, if you know it. Suppose we have a bunch of linear maps. But they are actually matrix valued power series in some formal parameter Z. Let's say they're invertible, where V and W run through the finite dimensional modules of A. So you can think of a quasi-triangular bialgebra producing you these linear maps. And let's just assume that for all triples of finite dimensional modules, we have the Young-Baxter equation. So this is the left-hand side, and the right-hand side is the same, but in opposite order. And so this is an identity for linear maps on a tensor product. But really they are power series taking values into such linear maps. Okay, and then let's say I fix a bunch of finite dimensional vector spaces. I can consider this object called transfer matrix. I take the trace over some linear space. And so I get, so this acts in V tensor V1 all the way up to Vn power series. And so this gives me, if I trace out one space, I get such an object. Okay? And because of this Young-Baxter equations, I have the following commutativity. For all these finite dimensional choices I can make. Sorry. Okay. So The example is key example. If I take quantum affine SL2, and I can take all these vector spaces the same, namely the two-dimensional module of quantum SL2, then you recover 6 vertex R matrix and some transfer matrix, and it gives you rise to the XXZ spin chain Hamiltonian, quantum Hamiltonian. Namely, because this power series T, V, Z, its coefficients are mutually commuting operators. And in this particular case, you can identify one of these operators as this Hamiltonian. And so you get, it embeds into a family of Hamiltonian, a family of commuting operators. Okay, and then at least in this case, but more generally, you can do, let's say, the algebraic beta ansatz to find eigenvectors of T, V, Z, and hence of this quantum Hamiltonian. This is kind of standard approach. And so let me make one remark. Let's say for many interesting algebras, if I have two finite dimensional modules which are irreducible, then this linear map R is actually a rational function. Not just any power series, but a rational function. And so if in this case, up to a scalar, you get a polynomial transfer matrix. You just kill the scalar, you pull it out, and you redefine the transfer matrix. Okay? And so Baxter's Q-operator is, roughly speaking, an alternative to this algebraic beta ansatz, an alternative method to diagonalize the transfer matrix. Okay, so what do we need? We need some complex vector spaces. We need two polynomial operators. This is, if you like, the easiest case, although it can be done more generally. And we assume they're diagonalizable. And then they commute in various combinations. And finally, this is kind of, in some sense, generic conditions. And finally, we require a particular functional equation, which is quite a simple one. So I can look at the product of T and Q, and this should be expressible as a linear combination of shifted Qs. So here, these are, let's say, some scalar valued rational functions. And Q is just some non-zero complex number. Okay, so why is this interesting? You get an equation for the eigenvalues of Q, namely they are polynomials and they satisfy a certain functional relation, basically the same equation. And then setting, because it's a polynomial, you can set z equal to a root of this polynomial. There's finally many of them, and we get a system of equations for the zeros of the eigenvalues. Okay, and so this corresponds to the same equations that you get from this algebraic beta ansatz. These are so-called beta ansatz equations, at least for the models where this thing is applicable. Yes. 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 They are very special. Yes. Yes. So in practice, at least in my story, we will construct first alpha plus and alpha minus, but then we are kind of lucky in some sense to have a solution. Yeah. Yes. However, sorry, I wrote the Young-Baxter, just the usual cubic relation. Yes. This is special, but in the context of the representations of quantum affine algebras, it's a general feature. So these are nice algebras, let's say. They have this property. Yeah. They have that indeed, but that would not be enough, I would say. It's still very special. Yeah. Correct. Anyway, so once you have this system of equations, you can potentially solve it. And so what you get out of this is information of the spectrum of this operator. And so then you can find eigenvectors of Q and T. Okay, and so the historical note is that Baxter came up with this in the 70s, kind of very beautiful approach, very intricate. But it wasn't directly generalizable. It was kind of ad hoc approach. And so many decades later, people came up with a representation theoretic approach. And so this was Bajanov, Lukyanov, Zamolodchikov. In the 90s, this was for conformal field theoretical models, although clearly the approach was more applicable, more widely applicable. And so the idea is as follows. So recall that the transfer matrix is actually trace of some factorized expression. And so let's assume that we can also write the Q-operator as the trace over some vector space of some factorized expression. So basically a linear operator that acts on W tensor, a big tensor product. But here, W is an infinite dimensional vector space. And so V1 and Vn, they are still finite dimensional modules of some algebra. So let's restrict to the case where we have an affine quantum group. But let's say that, so how does this W then fit in? So W cannot be an infinite dimensional module of this affine quantum group, but it will be an infinite dimensional module of some subalgebra. And so the module structure of W, it doesn't extend to the whole quantum group. We will make it more explicit later on. And so let's see. Yeah, from now on, make a simplifying assumption. I will just look at the case that all these V's are the same, and they are the same as the vector space appearing in the transfer matrix definition. And so suppose they are simply a two-dimensional module of my quantum algebra UQ SL2. So I will write UQ G hat, but I will also always mean quantum affine SL2. Okay, so how does this arise? Yes. Thank you. So G hat is a central extension of the loop algebra of SL2. And so because of this, it has certain generators, which are simply loop generators. So you have the notation that X sub M, superscript M, is basically X tensor T to the M, where X is an SL2 and M is an integer. And then there's a central element. Okay. And there's certain relations, but you can rewrite those relations in the kind of Kac-Moody style. So you get just two SL2 triples satisfying Kac-Moody relations. So this forms an SL2 triple, and this forms another SL2 triple. And the relation is as follows. Let's see, let's go here. So we have so these two SL2 triples. So E1 is simply E tensor T to the 0. F1 is F tensor T to the 0. H1 is H tensor T to the 0. And then for the ones with label 0, we swap the role of E and F, and we have different and this final H0 is basically the central element minus H1. So there's a kind of dictionary. Okay, and so you can show that these new generators satisfy Kac-Moody relations. That is to say, they satisfy relations akin to the Chevalier-Serre presentation of finite dimensional semi-simple Lie algebras. Okay, and so this G hat it embeds into a larger Lie algebra, which is an extension by derivation, which is the actual Kac-Moody algebra. So this D corresponds to, so conjugation by T corresponds to T ddt in this, on this loop algebra, centrally extended loop algebra. And so this is a Kac-Moody algebra, and so it has a non-degenerate linear form. Okay, and so this inclusion can be Q-deformed. So rather, for the universal enveloping algebras, it can be Q-deformed. And so what you get is an embedding of quasi-triangular bialgebras. And so here Q is a non-zero complex number, not a root of unity. And so these relations that are satisfied in the centrally extended loop algebra, they have analogs in the Q-deformed world. And so there's, let me write them down. Let me write some of them down. So the capital EI is, roughly speaking, a direct analog of the lowercase EI. Okay, and so these are so-called quantum SL2 relations. And the Ki is a new element corresponding to Q to the H, roughly speaking. So, and these are relations where I is either 0 or 1. So each quantum SL2 has their relations, and there are cross relations, which I won't give here. Okay, and so I should say Qi, you can think of it as Q to the Hi as a motivation for these relations. Okay, and so this is a well-studied algebra. And let's see. It has nice representations. So it's a bialgebra. And so in particular, there's a map from UQG hat to its tensor square. And so it allows you to consider tensor products of representations. So if V and W are representations, let's say, actually, let me write it like this. Pi V rho W. So pi and rho are the actual maps. Then I can define the representation. Sorry, let me call it. Sorry, it's a slightly different notation here. Pi subscript V and pi subscript W. Then you can define the tensor product representation. It's basically the tensor product of the representations that is actually a map with domain tensor square. And so you first apply the coproduct. Okay, so this gives you a module structure on V tensor W. So we have V tensor W. It's also a representation of UQG hat. Okay, there's a rich class of finite dimensional representations. And finally, we want to say something about R matrices. UQG tilde, which is the bigger version, is quasi-triangular. And in particular, in this case, it means that there is some element R, which actually lies in a particular subalgebra, but I mean, for now, let's say it's acts on tensor products of certain subcategory called O of this algebra, which I won't explain precisely, because we'll repurpose this R matrix, such that satisfies the axioms of a universal R matrix, taking into account the subtlety that it doesn't lie in the algebra, the tensor product of the algebra itself. Okay, so this is a linear relation, and you have two coproduct formulas. So these are relations, these coproduct formulas are relations in the tensorial, in a completion of the tensorial cube of the algebra. So you need three subscripts, three different subscripts. So this is for the bigger algebra. So this quasi-triangular structure comes from this non-degenerate linear form, essentially. And then how do we let it act on these finite dimensional modules, such as this tensor product of two-dimensional modules we're interested in? And this is how this formal parameter appears. Namely, I can extend my scalars. I can tensor with, for instance, Laurent polynomials. And this sigma z is a map, which is actually a bi-algebra automorphism of this algebra with extended scalars. It's a very simple map, like this. So this is defined in terms of the so-called principal grading. And then there's some sort of analog of the Cartan subalgebra, where it acts trivially. Okay, and so with this simple gadget, you can define this graded or shifted, I should say, shifted universal R matrix. And this acts with some kind of careful check. It acts on tensor products in finite dimensional modules of UQG hat of this slightly smaller subalgebra. Okay, and so the example is if you define a two-dimensional representation as follows. So simply, you can let E1 and F0 act as this standard SL2 matrix, F1 and E0 as its transpose, and K1 and the inverse of K0 is a diagonal matrix, which is just Q to the SL2H. Then you get, using this formalism, the 6-vertex R matrix. Let me go over there. Okay, and so I will set, I'll define a representation of the algebra by first introducing this grading shift. And so you get a so-called shifted module structure, which is abbreviated, instead of V, you can write V subscript Z. And then you will get, for the R matrix, so that's basically the, if you like, pi Z tensor pi of the universal R matrix. And you get scalar times the 6 vertex R matrix. So in these conventions, it looks like this. And here we have. And this element appears here, and this is here. And so this is a power series. Okay. And then you can make a remark that this universal object, which is grading shifted, actually acts on a bigger category, a bigger class of tensor products. So basically you can take, without going into too much details, take almost any, but let's say a suitable representation of a subalgebra, which is sort of the Kac-Moody analog of the Borel algebra, which is simply the thing with generators E0, E1, K0, K. And you can also take a representation of its opposite, which has E replaced by F. And then still you have a well-defined action as power series. So you get this RZ acts, let's say this is W plus, W minus, as a linear operator valued power series. Okay. And so the Q operator can be seen as arising in this fashion. So let's look at a particular representation, which is an infinite dimensional vector space, first of all. And then it's defined in terms of certain very simple operators on this vector space. So you have an operator A, which is just lowering the index of my basis vector. And so in this with this notation, I also mean that A of W0 goes to 0. And then there's an operator A dagger that increases the index, but with a scalar factor. Okay, and so these are two linear operators on W that satisfy the defining relation of so-called Q oscillator algebra. So you have, you can check it straight away, that A dagger A minus Q squared A dagger is 1 minus Q squared. And then you also have sort of, so let's say, diagonal operators. Let's say I have a function from the index set of my vector space to, let's say, this power series. Then I can set this notation. FD just means an operator which acts on Wj as f of j, Wj. Okay, and then you can define a representation. So this is the only one I will write down explicitly, but it's a representation of upper Borel. So E0 . basically acts like a dagger with some correction. E1 acts like A with a correction. And then K0 and K1 act as these diagonal operators. Like this. And so there's a slight freedom you have here with upper Borel representation, because there's not so many relations you have to satisfy. You can introduce certain scalar factors. Well, there's an extra parameter dependency here for some non-zero complex number. Okay. Yes. This doesn't extend to a representation of the whole algebra. It's impossible. It extends to a representation of a larger subalgebra, which is also called asymptotic subalgebra. This is called asymptotic representations. You can motivate them, roughly speaking, by taking a limit of finite dimensional representations. You can take this limit, but you cannot then keep the action of F0 and F1 as part of your limit. Maybe, but you can. I'm just saying you can write down explicit formulas for the finite dimensional representations. Asymptotic in the sense that I can take the limit of the dimension. Okay. Yeah. Kind of, in a certain way. Yes. Kind of. Yes. Yes. For sure. And so more generally. Sorry? Yes. And so more generally, this can be done for any quantum affine algebra. You can consider such asymptotic representations. And the key reference for this, well, there's two, Hernandez and Jimbo. In 2012. And then the application to Q-operators was done by Frenkel, Edward Frenkel and Hernandez in 2015. There's many more interesting papers that came out of that actually, but both in terms of the quantum affine quantum group. Yeah, yeah, and you get also all sorts of beta ansatz conditions from this paper that match. No, affine quantum groups, affine Cartan matrix, and so on. Non-twisted, yeah, non-twisted. That's right. Yes. Okay. So we have now the UQB hat plus module on this structure, on this vector space W. So the representation is rho R, and then this is called W. This vector space, for abbreviation, let's call it WR for the module structure. And then I can look at the Z-shifted module, which I will call WRZ. And so that's just the vector space. And now I look at this, the representation map is simply first applying this grading shift. Okay, so I have these representations. And so now we can look at images of the R matrix. Get so-called L operators. In this case, they're called L operators for Baxter Q-operators. And it's simply the action of this grading shifted R matrix on W R tensor V. And so this is what it looks like. It's a fairly straightforward map. So it's a 2x2 matrix. I factorize it. This is the kind of easy factor, diagonal factor, like this with this element, this scalar R. And here you have if you like, a more non-trivial factor. And you get this kind of construction with raising operators and lowering operators. Okay, so this is a matrix values power series. In this case, it turns out to be polynomial. And so you can get this, and then you can define, if you like, the Q operator. But it goes via so-called transfer matrix with auxiliary space W. And it's something like this. So I label the auxiliary space with a 0 here. So this acts on the 0th and the nth factor in the big tensor product. And here it's all the way down to 1. So it's the same structure as a transfer matrix. Now, unfortunately, this doesn't converge as a series. This is a series because W is an infinite dimensional vector space. But if you include this factor here, acting in the 0th space, where zeta is a complex number with absolute value less than 1, then it does converge. And so you can think of this as some kind of twisted periodic boundary condition. And so here, this construction gives you essentially the desired properties for Q operators. Just double check. It's fine. Oh. And so, for instance, you can prove now that the original transfer matrix and this infinite dimensional version, they're diagonalizable for generic values of these parameters. And they satisfy all these commutation relations. And then the TQ relation arises via a short exact sequence. So you have, and this is the reason why I include this parameter R, little r. So you have a short exact sequence of intertwiners of UQB plus hat. So you look at the module W, where these parameters R and Z are shifted by a factor Q. Then there is a map iota. So the claim is such a map iota exists such that this is a short exact sequence, but you can make it explicit. And we'll do it in a second. It's an easy map, actually. And then there's a map tau, which is a surjective map going to a similar module structure, but now with Q inverse. Okay, so this is a short exact sequence. So it means that this is injective, this is surjective, and the image is the kernel, this one. Okay, so you can check this kind of explicitly. You can kind of solve it as an exercise if you like. And so this iota and these tau depend on this parameter R. And iota R just is a very straightforward, and you can represent it like this. And tau looks like this. These are really straightforward maps, and you can call them fusion intertwiners. So there's also finite dimensional analogs of these intertwiners for representations of UQSL2 hat. And you can kind of think that you can take the limit as the dimension goes to infinity, and then you get these fusion intertwiners for the upper Borel. Okay, and then using this relation, the universal R matrix, you get certain identities for L operators. Some scalar. And if you, the fact that such a relation holds follows from this fact that this is an intertwiner and the axiom of the universal R matrix. And then by applying it to a vector, you can find the scalar, and you get the factor 1 minus z squared. And something similar for tau. There's a similar relation for tau, which I don't give you. Okay, and then you can write down the formulas. You can essentially derive the TQ relation from this formalism quite easily from a very nice principle that given such a short exact sequence, a trace over a tensor product can be split if the middle, because the middle, the big vector space in the middle is a tensor product. And so, just to save some time, let me write down the result. You get the TW R Z TV Z, so it's a transfer matrix. You get some factor. Like this. Okay, and then you have to do one more step to get to the actual Q operator. And I'll just give you the definition. Q of Z is simply a correction of this transfer matrix with the diagonal operator acting on the tensor product at value with R equal to 1. And then you get some relation which is very similar to this relation straight away, and that's the TQ relation. Okay, and so you can then answer questions about Bethe-Ansatz conditions and diagonalizing the transfer matrix. And so let me just say some words about the open spin chains. And so we particularly, so this derivation of the TQ relation is not literally what appears in the papers by Barzhanov, Lukinov, Zamolodchikov, although you can kind of it's just the ordinary transfer matrix. Yeah, because here, this is the trace over W tensor V of essentially of this vector space. And because of the short exact sequence, I get here a trace over W QR QZ, and here a trace over the other side, W Q inverse R Q inverse Z. Yeah, absolutely. So it's basically part of the results of Barzhanov, Lukinov, Zamolodchikov. They did more. Part of their results turned into a different, slightly different formalism. And the reason why we did this is because we could generalize this formalism to open spin chains. And so the key ingredients for open spin chains, some new ingredients, is you have two boundary operators called K matrices. And so the K matrix, like one of them corresponds to this kind of reflection. And then there's another one for the other side. Like this. You can now build transfer matrices and also Q operators according to the following picture due to Skianin. So you have this n particles, and then you form an additional vector space here, which is a trace over various operators, namely not n R matrices as previously, but two n R matrices and these boundary operators. Okay, and so this very special solution. So in order for these to commute, you need these elements to satisfy boundary Young-Baxter equation. I will kind of sketch it here without spectral parameters. It looks like this, but it will be an equation, let's say in a tensor product, depending on some power series, so depending on some formal parameters. So K and Z, so there's two formal parameters appearing as arguments of K here. And so you can define transfer matrices that commute using this principle. And so one solution of that equation for the R matrix we considered is the one that was already studied by Skjanin, a simple diagonal solution where the new parameter psi appears, which, if you like, is a controls sort of the interaction at the boundary. Complex number psi. Okay, and so based on this, you can kind of generalize this this whole procedure. And so maybe I'll say a couple more things about the representation theory idea behind this operator K. So K is like R. Turns out, with benefit of hindsight, that KR is also the action of a universal object in an algebra. So KZ, that simple two-dimensional matrix, but many of its bigger brothers as well, KZ is basically the image of some universal object. Satisfying universal relations. So I'll mention two important relations here. So remember, kind of to contrast it, the R matrix satisfies this relation, linear relation, for all elements in the quantum group, UQG hat. The K matrix satisfies some kind of similar equation for a subalgebra. I will call capital B. So the subalgebra, you can think of it as a boundary quantum group. So if the quantum group contains the symmetries of a family of related models, the boundary quantum group contains only those symmetries which are compatible with the new boundary conditions you can impose. So this is a subalgebra, not the whole algebra. So I should write it like this. Not the whole algebra. Subalgebra of UQG hat. Okay, and so this psi is a certain automorphism. It's a very simple one in the case of that K matrix. It's an involutive automorphism. Okay, it's a very special case, and you can find this universal object. You can define it in this way with this linear equation, and then you can look at the image of this linear equation in representations and use some nice symmetry properties of this particular choice to show that that 2x2 matrix must be the image of this universal object. And so this more general picture we discussed in work with Apple in 2020, 2022. There's a kind of parallel story of universal R matrices that also apply to K matrices. And you can get identities out of it. And so in particular, using some axioms of this universal K matrix, I'll mention one kind of concrete benefit that you can get from it is namely that you have this relation of L operators as a counterpart for K operators. Here we go. So I can define K matrix acting on infinite dimensional vector space, which will also depend on this parameter R and the spectral parameter Z. And then you have this L operator. Then you have this 2x2 K matrix. And so you can ask what happens if I put this intertwiner iota into such a combination. And because of the axiomatics of universal K matrices, there's a scalar factor, which we know precisely. And out comes the infinite dimensional K matrix with shifted arguments. And then here is a modified version of this intertwiner. This is just basically the same intertwiner, but with the flip map, because otherwise the identity doesn't make sense. And so the picture for this, if you like, motivating picture, So you have iota. So this is the left-hand side, what I'm drawing now. You have iota coming from the bottom, from the top. Iota has this domain, infinite dimensional vector space. So I draw it with a fat strip, if you like, not just a line, but a strip. Then I can split off a finite dimensional vector space that interacts with the boundary. That's the factor kv. So it has z inverse. Sorry, qz. No, it's okay. Yeah, z inverse, and then it interacts with the infinite dimensional vector space. So this is this R matrix, the L operator, LRZ squared, and then this also interacts with the boundary. Okay, so this is the left-hand side. So you have another KW here. And so here, the incoming you have RZ, and outgoing you have R inverse, Z inverse. And then there's the right-hand side. So what is the natural picture to draw on the right-hand side? Well, first, you can interact, let the infinite dimensional vector space interact with the boundary. And then you split off this finite dimensional one like this. Okay, and so the parameters are compatible. And so this is the underlying picture behind this identity. And so once you have this, you can kind of play the same game as before, and you can derive a TQ relation for open spin chains. And so I think I'm out of time, correctly? Is it correct? I have some freedom, I see. Let me write down some open problems. And then there's something to discuss. So we can prove the TQ relation. There's some basic problems we can't solve yet. We don't know if QZ, defined by this picture, if I let this be the infinite dimensional vector space, W, polynomiality of QZ is not clear. We conjecture it. It can be checked for the diagonal entries. You can prove it. So although it's not clear, we're pretty sure it should be polynomial. Also, what is not clear is that Q commutes with itself for different values of Z. The usual argument for this commutativity, for these kind of pictures, goes back to Scianin. And so in this way, you can prove straightforwardly that T commutes with T and T commutes with Q. So the argument that T commutes with Q requires a little bit of a tweak of Scianin's argument. And that was given initially for the analogous construction for the XXX model. So I should at least mention these people. They are Frasek and Siechenyi. This was in 2015. So they did this construction for the XXX model, but without the representation theoretical motivation. But they were able to write down explicit formulas and show that all the identities hold. And so they, in particular, show that T commutes with Q using a version of Scianin's arguments. Maybe I should also, since I mentioned these people, I should mention one more pair of researchers, Bazayak and Tsuboy, from 2018. They already looked at Q-operators for the XXZ spin chain, but they didn't show the TQ relation. They have a nice theory of different kind of compatible versions of these operators. So for the KWs, let's say, the infinite dimensional versions. And so they are kind of, there's natural candidates, let's say, for nice, with nice properties, but they didn't show the TQ relation. And so that's one of the motivations for us to actually consider this problem as well, being the key relation. And so for other perspectives, other open problems. These are localized open problems for this particular model. Why more wider open problems? Yeah. So in Spirit they work, but the way he wrote it down, you'll end up taking a partial transpose over an infinite dimensional vector space. And you could probably, in certain cases, work with that, but yes, but so but it's very straightforward to, in his Spirit, write the argument slightly differently, so that the partial transposes only end up on the finite dimensional vector space. It's kind of tedious, but it's quite nice in the end. Yes. So if both are infinite dimensional auxiliary spaces, then of course that argument still doesn't work, and then we need some kind of. What the idea is that you have some universal expression for the thing inside the trace, but you can't just use a single K matrix. You have a product of two, one for the left, one for the right, and then apply the representations, and then deduce commutativity. And we all, yes, well, so this has been checked at least for low values of n and for the diagonal entries, but it's quite a bit harder to do it with these new ingredients KW. They're not polynomial in Z. Mm-hmm. Mm-hmm. There should be two solutions. So this is what I was going to write down actually. Wide opposed. There are two solutions. So there's a Q and a Q bar, let's say. So they satisfy the same relation. So two solutions of the same equation, the TQ relation. So roughly you can think, well, this is a second order difference equation. So if you're lucky, you have two solutions, but because they're polynomial, it's an extra requirement. You're very lucky that you have both of them. And so, but this is definitely true for the closed spin chain. And the idea is that you simply have a different, yeah. Yeah, I think in the simplest case, it is polynomial. Both are polynomial. Yes, but it's a good point. We don't have the polynomiality of the other one for the boundary case. So it's a good point. So the idea of the second one is simply you take the trace over a different module. It's the same underlying vector space, but a different module depending on a different representation. So here we use the representation rho. And here you have a different representation, let's say rho bar, of the same upper Borel subalgebra. And then for the closed case, you can make it's quite easy to develop the theory in parallel for the second Q-operator. And then you can actually prove nice properties, such as you can take the products of two Q-operators with shifted powers of Q. Sorry, with the parameters shifted by powers of Q. And then you can reproduce the transfer matrices of the finite dimensional vector spaces with the finite dimensional auxiliary space. And so we were trying to do this also for open spin chains, but because this guy is quite a bit trickier, it doesn't yet work. However, we do have a kind of a partial result, which is, well, it's kind of promising. So I won't, to write it down is a bit trickier, but basically you have some factorization identity involving intertwiners between the tensor product of these two representations with the tensor product of the loop Verma module with a trivial representation. So you can use this to kind of get part of the way down. But certainly this is still out of reach. Yes. Time, let's stop here. Thank you very much.
Any comments, questions?
So they arise. Oh, sorry. So they arise when you move this iota through products of L operators, R operators. Yeah. Oh, for the. Oh, I can tell you the precise formula. Yeah, I'll tell you. You wanted to know the precise formula. I forgot. It's very similar in spirit to the original alpha plus and alpha minus. Oh, here they are. Where shall I write it? Let's give it their due space on the blackboard. Okay, so these are the coefficients that appear in the TQ relation. Alpha plus. So we have this factor. This is kind of some kind of artifact from the fact that you have a solution of some reflection equation on the other side, which is not the natural one. In some sense, you have some kind of correction. It's not super interesting in this sense, but you have two factors related to the K matrices. So for the left one, which I called K tilde, I didn't talk about it very much. There's a similar expression like that with a parameter psi tilde. And then for the right, which is that one, you have this. So it's very symmetric between those two. And then you have contributions for the bulk. So you have two N R matrices. So you get this. That's the one. The other one, see, you have Q to the 2N. Then you have this kind of business. And you have two factors corresponding to this. And then you have these guys, but then now they're shifted by Q squared.
In the upper line for alpha plus, Q missing to the last step?
No, that should not be a Q. This is correct. There's maybe maybe you wanted to shift all the Z's by a factor of Q or something like this. If you wish. But these produce the beta Antas equation that Scianin found. No, just this one, and its brother on the left hand side. Just this one. Oh, I don't know. But let's do it. Let's try it. So for the more general one with non-diagonal entries, you have two essential parameters. Sorry, this one has one new parameter. The other one has two essential parameters, not one.
Okay.
So this might be interesting. Yes.
Universal relation can be independently exist because this is K equation, right?
Yes, this is correct. So in this universal world, you think of it, it's in the algebra, but really it's in the class of all suitable representations of this algebra. So but you can check using kind of let's say homogeneous arguments, with respect to all these representations, that there exist certain solutions of certain recurrence relations that exist, even though you don't know them explicitly, but they exist. And it allows you to solve these linear equations for the R matrix and for the K matrix as well. And then you observe the other axiomas like coproduct formulas you observe from these formulas as well. Yeah.
Somewhere secret here, there should be co-ideal.
Yes, I didn't say the word co-ideal, but so I mentioned something about a subalgebra B, and this is the co-ideal. So it means, I'm glad you mentioned it. So this is a subalgebra, but it's not a sub-bialgebra. So you have the following relations. So this is for the right-hand boundary. So that means the bulk is on the left. So it's a left co-ideal. That means this relation. That means, in particular, if I have a representation of the bulk and I have a representation of the boundary, with the coproduct, I can get a new representation of the boundary. That's why it's important. Although, in some sense, you could give this story without mentioning this. It's nice to kind of add it to complete the picture.
Yeah.
Representation of this boundary on the front.
No, W is the same as before.
So it should be something which is the same type.
It's a representation of the upper Borel. No, 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 no. This is a big complication. The boundary algebra B is not contained in the upper Borel. The intersection is almost trivial. Yes. I'm saying that K lies, well, what I should have said is that this universal K can be chosen to lie in the upper Borel completed. So its actions are compatible with UQB plus interplanars. Yeah. That's the axiom I should have written down as well. Delta K. So in that particular choice, for this particular very nice, simple solution, it's a threefold product. So it's something like K tensor 1 tensor K. So it's almost like a group-like element. But then there's an R matrix, which is twisted by psi in one leg. This is a universal statement. But I don't know, because I don't know how to write a Q-operator universally. Not yet. If you have ideas, we should discuss.
Okay. Any other comments, questions? Ivan. Okay.
In terms of look for things DJ or
The answer is yes, but can I reproduce this right here? What you can certainly do is you can write on this transfer matrix. So with the auxiliary space, just the two-dimensional space, you can, in the same way as for the closed chain, you can define a quantum Hamiltonian by taking, roughly speaking, a derivative or logarithmic derivative of that object at a special point. And then you can read off the usual spin chain nearest neighbor interactions plus two boundary terms which are diagonal, and they roughly correspond to these K matrices. So one depending on psi and one depending on psi Q. So you have this. Yeah.
Okay. Let us thank our speaker again, and we will have one more talk tomorrow about Q-operators for the Roussillard systems. Sorry, one comment, please. Don't go. From in December, we will have a workshop about integrable system in Peking University from 23 to 25 December. And we have one free slot. Yes, Nikolai, yes. One free slot for the speaker from the BIMSA. If you want, you can say about it to Nikolai or to me.